Hello everyone! Today I will teach you how to draw the graph of a derivative. For introductory purposes, firstly we need to clarify the difference between the derivative and slope. Even though we may often use them interchangeably, there's a difference between them. The slope refers to the property of a line. If a function is linear, so it has either one or two variables without exponents, such as the example on the left, it will have a slope. However, for a non-linear function, we don't find a slope. We do actually take a point on a graph of a function and draw a tangent. Like here. This tangent is a line which touches the curve only at one point, and because it's a line, it has a slope. The slope of the tangent line at a point can be found by taking the derivative of a function and evaluating this derivative at x being equal x value of the point. The answer for the example not only provides the slope, but the equation of the tangent as well. The definition of a derivative utilizes this fact, as it says that the derivative of the function y equals fx at the point x0 is the slope of the tangent line to f at this point. So the derivative gives us a formula to find the slope of the tangent line, not the slope of a function. Now we will learn the basics of graphing using the example of a quadratic function. The parent function of this graph is minus x squared plus 2. The derivative of minus x squared plus 2 is minus 2x. Therefore, the derivative is a linear function. So the derivative has a slope of minus 2. However, we need to analyze the parent function's slope, as the derivative gives the slope at any point x. On the left side, the function is increasing, which means that the slope is positive. However, when x equals 0, we have a horizontal tangent line. At that point, the slope is also equal to 0. Why does the horizontal tangent line occur at x equals 0? Because horizontal tangent line occurs at a maximum or a minimum, and slope of any horizontal line is 0. And at x equals 0, we have a local maximum. On the right side, the function is decreasing, which means that the slope is negative. Now, let's graph the derivative. When x equals 0, the value of the derivative will also equal 0, because that's where the parent function local maximum is. The slope of the parent function is positive on the left, that's why the derivative's left side y values will also be positive. The slope of the parent's function right side is negative, so will be the y values on the right side of the derivative. This exemplifies the fact that the slope of f becomes the y values of the first derivative. As you can see once again on this example, when fx is increasing, the y values of the first derivative are positive, and when fx is decreasing, the y values of the first derivative are negative. Now, what about the second derivative? How to graph it? If the first derivative is minus 2x, then the second derivative equals minus 2. That's why we are going to draw a horizontal line at minus 2. This decision can be supported by the fact that the slope of the first derivative is constant. It's always decreasing, with its slope being minus 2. What's more is that you may think that whenever the second derivative equals 0, this will correspond to something called an inflection point. That's not actually the case. It represents a point where an inflection might exist, such as here and here. Only if the second derivative equals 0 at a point x and changes sign when passing the point x, then we actually have an inflection at x. The point of inflection indicates where a function changes from concave up to concave down and vice versa. On the left side, we have the previous example, and as you can see, the second derivative doesn't change the sign after passing the point where x equals 0, which means the original function doesn't change its concavity. On the right, we can clearly see that the second derivative changes the sign after passing at the point, which confirms that there is a change in concavity in the parent function. Moreover, we can deduce that because the function changes from negative values to positive, we have a change from concave down to concave up, so the parent function would look like this. To reiterate, if the parent function is concave up, it means that the second derivative is positive. Therefore, the intervals on the second derivative that are positive correspond with the intervals on a function that are concave up. As seen on the example, none of the intervals indicate the concave up look of the function, simply because there isn't one here. However, if the parent function is concave down, then the intervals on the second derivative that are negative must correspond with the intervals on a function that are concave down. As you can see, the entire second derivative is negative, as the entirety of the parent function is a concave down curve. The basics we just learned can be applied in the same way when it comes to the cubic function. The parent function is x cubed and we have a horizontal tangent line around 0, which means the slope there is 0. The first derivative, 3x squared, both of the sides of the parent function are increasing. Therefore, all the y values of the first derivative are positive, and it looks like this. What's worth to reiterate again is that whenever we have a horizontal tangent line where the slope is 0, the derivative of the function will have a y value of 0, an x-intercept. The second derivative equals 6x. The left side of the first derivative is decreasing, so the y values on the left will be negative. The right side of the first derivative is increasing, so the y values on the right will be positive. Now, it's time for the second example regarding the trigonometric functions. Firstly, we will look at a sine function. The derivative of a sine x is cosine x. Now, the first step is to identify where the local maximum and minimum are, so where the horizontal tangents occur. So, we have here and here. And then marking them on the derivatives graph. So, here and here. Between minus pi over 2 and pi over 2, the function is increasing. So over that interval, the first derivative's values will be positive. Between the intervals minus pi to minus pi over 2 and pi over 2 to pi, the function is decreasing. That's why the first derivative's values in these intervals will be negative. So here. The same steps can be applied in the case of a cosine function. The derivative of cosine x is negative sine x. So we mark the maximum and draw the curves whether they are positive because the function is increasing or negative because the function is decreasing. So here the function is increasing and here the function is decreasing. Now, it's time for the third and the last example, rational functions. Just like before, all the basics we learned still apply even though the functions look a little bit different due to the horizontal and vertical asymptotes. Firstly, we will look at the 1 over x function. It may not be obvious at first sight, but the left side of the parent function is decreasing as it's going to 0. In this interval, until the vertical asymptote. On the right side, the parent function is also decreasing. Therefore, the derivative minus 1 over x squared will have negative y values on both sides. But while drawing, we still need to have the vertical and horizontal asymptotes in mind. The same goes for the other example. 1 over x squared function. It's important to remember that the fact that all of the values of this function are positive doesn't matter. We need to focus on the fact whether the function at these intervals is increasing or decreasing. So on the left side, the function is increasing. And on the right, it's decreasing. Having in mind the vertical and horizontal asymptote, the derivatives graph will look like this. That's all for today. Thank you for your attention.